the waves. Let's very quickly run through the basics of the waves seen on an ECG and the key factors you need to look out for. First wave here is a P wave, and it represents atrial depolarization. This is followed by a QRS complex, which represents depolarization of the ventricles. The important part here is that you need to look at the relationship between a P wave and a QRS complex. For a heart rhythm to be called sinus, each P wave should be followed by a QRS complex. This signifies that the rhythm of the heart is being generated by the sinoatrial node. The next point is how many P waves does it take to generate a QRS complex. If it's taking many P waves to generate a QRS complex, it could signify something called atrial flutter. The third point here is the duration between a P wave and a QRS complex. This is called PR interval. A normal PR interval is between 120 to 200 milliseconds. Anything longer is significant for an atrioventricular block, otherwise known as AV block. To calculate the PR interval, you need to count how many boxes are in between the start of a P wave and the start of the QRS complex. Each small square on an ECG paper horizontally is 40 milliseconds. Hence, 5 small squares make one big square, which equate to 0.2 of a second. Therefore, we could say that a PR interval needs to be between 3 to 5 small squares. The QRS complex needs to be less than 3 squares, or less than 120 milliseconds. Vertically, we are measuring electricity, and each small square is worth 0.1 millivolts. The next and last wave we'll talk about is a T wave. A T wave is repolarization of the ventricles. The important part here is a segment between the QRS complex and T wave called ST segment. In a normal ECG, ST segment should sit at the isoelectric point. The isoelectric point could be thought of as a baseline for an ECG. It's a flat line where no electricity activity takes place. So far we've discussed everything being normal on an ECG strip. Later on we shall discuss what it means when something doesn't follow the patterns we have just discussed. Limb leads. Now we are going to move on to looking at actual ECGs. However, our focus at the start is purely interpreting limb leads. We shall move on to chest leads in the later part of this video. Each ECG will be up for 7 seconds. You may certainly take more time than that by pausing the video whilst you interpret the ECGs. When interpreting ECGs, some of you may jump to a method known as spot diagnosis. However, with spot diagnosis you may miss something very obvious. Instead, it's useful to have a system or an order to interpret an ECG. A good order to follow would be rate, rhythm, presence of P waves, PR interval, QRS interval, any ST elevations, T wave inversions, and then look at the cardiac axes. And the answer to some of these questions can be answered by just looking at the limb leads. So let's interpret the ECG in front of us. We are going to look at the bottom lead, which is a rhythm strip of lead 2. It just allows us to see one lead for an extended duration. To calculate the rate of this ECG, we choose 2 points on adjacent heartbeats. It is easy to choose this point as the R wave and determine the RR interval, as it is a very distinct point on an ECG. Now we've chosen 2 points, we count how many big boxes are in between the selected R waves. In this instance, it's 3 boxes. Now we divide this number by 300, giving us 100. The reason why we divide this number by 300 is because each big square is equal to 0.2 seconds, hence 300 big squares are equivalent to 1 second. So the rate here is 100 beats per minute. As you get more experience looking at ECGs, you will be able to tell if a rhythm is regular or irregular. But a methodic way in which we can determine the rhythm is very similar to how we calculate the rate. determine the RR interval and now see if the RR interval remains exactly the same throughout the lead strip. The RR interval in this ECG remains 3 boxes throughout, so it's a regular rhythm. P waves are present here. Due to the quality of the ECGs, it's hard to give a precise number for the PR interval. However, it seems to be 4 to 5 small squares here. QRS complex appears to be 3 small squares. Now we can start looking at all of the limb leads to check for any ST elevation. All ST segments are sitting at the isoelectric point, so we can say that's not elevated. There are no T-wave inversions. However, some of you may say that the T-waves in AVR are inverted. However, if you remember, AVR is looking at the heart from the right side, making all waves negative. Given a negative lead 1 and positive 2, 3, the axis is deviated towards the right. Therefore, based on our interpretation of the limb leads, we can say the ECG is normal. There still might be some pathology in the chest leads, which we will cover later.